Okay, this is homework video 9, 14, or 15. Hopefully you have that blank handout or you could print out one of your own. I want you to watch the video and fill in the numbers here. Turn this in the day before your test or the day of your test. So here we go. For periods 1, 3, 5, test is Monday. Periods 2, 4, 6, 7, test is Tuesday. Here we go. Adding 3, as soon as I see that I'm adding 3, I know this is arithmetic. It's going to be a straight line graph right away as soon as I see that plus. As soon as I see that plus 3, I could use that to write my recursive equation. So here is my recursive equation with that plus 3 right there, because I'm using every one before it and adding 3 to get the next one. Here we go. Here's that formula in play. To find this blank, use the one before it and add 3. 10 plus 3 gives me 13. To find this blank, use the one before it, which is 13. Add 3 gives me 16. Be careful though. Don't keep adding 3's here because this is jumping from 5 to 24. It's not the sixth term. I can't just keep adding 3's. Now I have to use a formula. I could use that 3 to go backwards in this table and subtract 3 from this 4, and that gives me the y-intercept, which is 1. So my recursive forms, here I go, are explicit. F of x always equals that number that you're adding in front of x plus that y-intercept number right there, plus 1. I could use that to plug in any number for x. The other one, of course, is using the first term one, which is that same 3, but in parentheses timesing x minus 1, and then plussing that 4 right there. You could write it like that. But just be ready, Mo. You could also flip this around if you want. You could have wrote that 4 plus that same 3 right there times x minus 1. Remember, both those are the same. Those are equal. But then remember, if I take this and I distribute, that gives me 4 plus 3x minus 3, and that 4 and that 3 combine to give me 3x plus 1, the same as this. So that means both of these, the first term 1 and the zero term, they're equivalent. They give you the same value when you plug it in. So just know you could plug it in to both the zero term 1 or the first term 1, and then just don't freak out by knowing that that could be flipped around. All right, here we go. Plugging in that 24. This 24 is going to go right in here where x used to be. So when I do that, I write f of 24. There it is already. I could just go ahead and go 3 and put right there the number that I'm plugging in and timesing, which is that 24. And of course, I'm going to times that and add that to 1. What we'd like you to show is every little step as I go down that I'm plugging in f is 24. So this next step, right, f of 24 again. And then times 3 and 24. 3 times 24 gives me 72. And then I'm going to add that 1 right there. 72 plus 1 gives me, when the x number in this function is 24, the y number is 73. That goes right here. And then know that last one is me having you take 121, which is the y spot, and plugging it in not for x, but where that y coordinate used to go. So here I go. So when I plug in 121, I write the 121 first, and I set that equal to the equation that it's equal to. If you want, you could flip that around to get it into an equation you're more used to looking at. And then right there, the opposite of plus and 1 is subtracting. If I do that, I got to do the same to the other side of my equation. That gives me 3x. Oops, I'm sorry, that's 121. When I subtract, that gives me 3x equals 120. And then right there, the oppo of timesing by 3 is dividing by 3. So that tells me when y is 121, x gets spit out as 40. So I'm going to put 40 right here, because what's that telling me is when I plug in x is 40, y gets spit out as 121. This one right here is telling me when I plug in 24 for x, y gets spit out as 73. Remember, these are all coordinates that we're doing. Sometimes we give you the x to plug in and solve for y. Sometimes we give you the y number to plug in first and solve for what the x number was at that spot. Now you need to graph. Knowing that graphing, this is the normal x-axis. This is the y-axis, but we don't call that y anymore. We call that fancy f of x, but it's still like the y-axis, still plotted the same. All of these coordinates give you coordinate pairs to plot. So this first one is 0, 1. The second coordinate is 1, 4. That's where I'm getting these coordinates to plot, kind of like an xy, even though y is now f of x, still kind of like y. So here I go. 0, 1 is right here on the y-axis. Over 1 up 4, right here. Over 2 up 7. Over 3 up 10. Over 4 up 13. I could backtrack this, left 1 from here, down 3 right there, negative 1, negative 2. That is also on that same line. Draw a line through these points, nice and long. Never leave the points without a line drawn through them if we're doing an explicit equation. And then I need you to draw arrows on either side of this line, but then understand what we're trying to get to you here. This is the y-intercept. That's 0, 1, just like it says on the coordinate in the table. This slope, or the slope of this, which is rise over run, matches my number that each time I go over 1 for x, I'm going up 3 for y. Every time I go over 1 for x, the y number is going up by 3. That's what that's telling you. All right, let's move on. The geometrics. So for this guy, it's not arithmetic. This one, I'm timesing by 2. That makes this geometric. It makes this one of these curve graphs like this, or one that goes down. Those are these exponential graphs. So here we go, recursive. I know enough already to write my recursive form, which is f of x equals f of x minus 1, and I put that times 2 number right there. That is my common ratio number, they call it. If it's adding or subtracting, they call it the common difference. If it's timesing or dividing, common ratio. I could use that to fill in my table. This 4 times 2 gives me 8. 8 times 2 gives me 16. 2 timesing by a half, which is dividing by 2. I'm taking this 1 and I'm dividing it by 2. 1 divided by 2 gives me 1 half. Or if I took 1 and times by 1 half, remember, that goes over 1. If my pen lets me draw straight across, gives me 1 over 2. Another way of getting 1 half is dividing by 2. So those are my numbers I'm going to use. Explicit is f of x equals always that 0 term number times, never plussing, times that common ratio number raised to the x power. That is my 0 term explicit. My first term explicit, I use not the 1 half in that table. I use that 1 times that same 2. But if I'm going over 1 on the table, I go to the x minus 1 power. If I'm using that to plug in 8, I'm going to probably shy away from that fraction one and plug in 8 right there. So here I go. F of 8 equals 1 time, let's do that in black, equals 1 times 2, and I put that 8 right here where that x used to be, minus 1. That gives me the f function at 8 is still 1. Don't touch that 1. This becomes 2 to the 7th power. And again, you're timesing 7 of those 2's, 1, 2, 3, 4, 5, 6, 7, or you're using the exponent buttons on your calculator, I hope, instead. So 2 raised to the 7th power gives me 128. And of course, for this one, since I'm timesing by 1, that's not going to change that 128. It's going to stay 128. So I put that number right here above the 8, knowing that that is the coordinate. 8 for x, 128 for y. That's what that really is. All right, now the next one, plugging in 1024 into the f of x spot, the y spot instead. So if I write that, I got 1024. I'm going to use the one without the fraction, even though it's got x minus 1. 1 times 2 to the x minus 1. And now it has me take 1024 divided by 1. That stays 1024. So now I'm looking for the power that I could plug in right here for x and get 2 raised to that power to get 1024. So again, if you're good at my calculators and you just type in some numbers like maybe 2 to the 6, you'll see that 64, so it's not 6. Maybe you could do 2 to the 7th, see what 2 raised to the 7th is. That's 128, so that's not big enough. If I do 2 raised to the 8th, not big enough. 2 raised to the 10th, looks like that's the one. So if I do 2 to the 10th, that does give me 1024. So now I need to know what number can I plug in here and get 10. So of course, some people could say, oh yeah, x has to be 11. Some people have to take that x minus 1 and set that equal to the 10 number I'm trying to find, and then a little bit of algebra will show you that, yep, the only number that's going to work right there is if I put an 11 right there, because that would give me 11 minus 1, which would give me 2 to the 10th. So that means I don't put 10 right here. That would not be enough, because plugging that in would hack that down by 1. I need to put 11 or 11 right there. That's the number that goes right there. That is the coordinate 11 for x, 1024 for y. All right, now you need to graph them. So 0 up a half is 0 half right about here on my y-axis. If I go over 1, I'm going up 1. Over 2, up 2. Over 3, up 4. Over 4, up 8. Over 5, up 16. Knowing that you do not want to draw just this part of the graph because people make it end up looking straight. You want to have these curve down, but then extend your curve through the graph like that, because that's really what the graph is going to end up looking. Some people, by mistake, when they draw their graph, since they have just those points, they'll draw it like this, and it looks straight to me. So try to practice drawing your graph the way you know these really look. They are these J curves. They either slope down like this, or they slope up like this. Those J curves, exponential graphs. All right, let's move on. Next one. This one says, if I give you x is 3, that's exactly what this problem's doing. X is 3. Find the corresponding y number if you want to look at in terms of x and y. Because remember, this is x. This is technically the y-axis or f of x-axis. If I give you a 3, that means I'm giving you the x number. What is the y number? So you find 3 on the x-axis. You go up until you hit that line. And when you do, you look over, and the number that you're looking to cross over, that is the corresponding Y number. That is 9 right there. Or if I do f of 3, it gets spit out as 9. That's what that is. And of course, if I keep on going, if I look at -1 on the x-axis and look at my graph, it looks like that one as I cut over is 7. So that is 7 right away. F of -1 is 7. If I wanted to write that as a coordinate, that's -1, 7. F of -1 equals 7. What does F of 5 equal? So I go to 5 on the x-axis, look at that line, look to the left. Looks like when x is 5, y is 10. Or if I had to write that as a coordinate, that's the coordinate 5, 10. When x is 5, y is 10 from this graph. All right, now the other ones, when that number is not inside that parenthesis, that means the number we're giving you is the y number instead, and we're having you find what the x number is at that spot on the data or the graph. So I'm going to delete this, and then those ones you'll watch, I'm going to start not on the x-axis like those ones that I'm giving you the x number. I'm going to start on the y-axis because I'm giving you the y-axis number. So here I go. So find that 9, go to 9 on the y-axis, not on the x-axis, hit that line, and when you do, look down, and that's the corresponding x number. So when y is 9, x has to be 3. If I wanted to fill that in, that is f of 3 equals 9, x equals 3. That's what that is. All right, so here we go. Next one, giving you 7. Find 7 on the y-axis right here. Look left or right. And when you do, look down. Looks like that one has -1 for the x number. So when f of -1 equals 7, that's -1 for x. That's the coordinate -1. If I do 11, find 11 on the y-axis. Hit that line, and when you look down, that is the corresponding x number at that spot. That has to be 7. F of 7 equals 11. That x number is 7. All right, here we go. This one gives you the first term is 20. It's telling you to times by a half. Remember, that's dividing by 2 until you get down to the weird fraction things. So if I take 20 and divide it by 2, or take 20 times a half, gives me 10. If I take 10 times a half, or 10 divided by 2, gives me 5. But now it gets a little weird. If I take 5 and divide it by 2, it gives me 5 halves. Or if I take 5 and times it by a half, remember putting that over 1 and timesing straight across, that gives me 5 over 2. So when I divide 5 by 2, 5 halves. If I take that 5 halves and times that by 1 more 1 half, which is dividing by 2, that gives me 5 over 4. And if I take that and times it by 1 more 1 half, that's dividing it by 2, that gives me 5 over 8. Noticing that that 5 number on top is not changing, only the bottom number is changing. That's what makes values get smaller and smaller and smaller. All right, so those are my next 5 terms. All right, here we go. Using calculators. -63 is my first one. This is plus and not timesing. So if I take that -63, I'm going to add 17. Hopefully I've shown you how to make -63 on your calculator. Plus 17 gives me -46. Let's do that in black. And then again, don't clear it. Leave that -46 on your calculator. Don't clear it. Just hit plus 17. and you'll get negative 29. Don't clear it, just plus 17, and you'll get negative 12. Don't clear it, plus 17 gives me 5. Don't clear it, plus 17 gives me 22. So get in the rhythm of using these tools we're giving you. Taking negative 63, the first term, and adding 17 to it each time. Those are the next 5 terms. You can see what happens to the negative numbers when you add. They go down. All right, here we go. Last one. Counting squares. So I have in my first step, 1, 2, 3, I have 4 white squares. In my second step, 1, 2, 3, 4, 5, 6. In my third step, 1, 2, 3, 4, 5, 6, 7, 8. I have enough to answer this multiple choice question because I could see that I'm plussing by 2. I'm adding by 2. I'm looking for all the equations with that 2 in front of x. I could see right here, there's a 2 in front of x. That one is good. I could see right here the 2 that I add each time I'm doing this sequence. That's recursive. That's good. I could see right here, this in front of this x is a 2. That one's good. But when I look at this bottom one, even though there's a 2 right here, that don't matter. Right here, I have a 4 in front of its x. You would never put any other number that's not the plus number in front of x. That is no good. You cannot do that. This 4 is okay because this still has 2 in front of x. So that bottom one is the one that does not describe this pattern. The other ones do. So I could use those to plug in 25, and I'm going to suggest using probably the easier of the two, that one right there. So if I want to find how many squares after 25 steps, I show it like this. I take that 2, and where there's an x's, I put 25, close that. I got plus 2 right here. That gives me the function at 25 equals 50 plus 2. That gives me the function at 25 equals 52. So how many white squares? 52 white squares after 25 steps using this pattern right here, 2x plus 2. And again, for those you want, again, how I'm getting those equations, 1, 2, 3, this is 0. Taking away 2 gives me the y-intercept of 2. Here are my equations. Remember, here's recursive. Here's explicit. Here's first term explicit. So you can see that's where we're getting these equations. They're legit. You gotta trust us. Those equations are legit that we're giving you there. All right, hopefully this helps. Copy it down. Take time to do other work that's due before the day of the test. Good luck. See ya next week.